Alright guys, today we're going to talk about sig figs and scientific notation. Ooh, let me get it back on the screen. Here we go. Starting off with sig figs. So what are sig figs? Well, when we are in lab, it gives us an ability to express the accuracy of the numbers and data we are getting in lab. So it gives us a way of expressing accuracy of our lab equipment. I'm going to segue off real quick and talk about accuracy versus precision and really what that word means. Accuracy means how close you are to the actual measurement. So how close to actual measurement. So if I think about a target, I have a target here. Of course, the middle would be most accurate. The closer my data is to that center target, the more accurate. The farther away, of course, is less. Now, some factors in our lab that affect accuracy are we can think about calibration, the tools that we're actually using, any procedures that we're doing, and of course, one thing that we never think about is our eyes, okay? So if I look at this piece of equipment, it has various lines on it, okay? They're far apart. They're not as accurate to give us an actual reading. Whereas if I look at this, I'm more accurate here because I have more lines. So it also can depend on the piece of equipment. The other thing is precision. Now, precision is the ability to repeat a piece of data collection. So, for example, let's say I shoot one arrow and it lands here. If I shoot another arrow and it lands here, the precision between these two, they're very close together. Okay, so here I would have good precision. Do I have good accuracy? No. Okay, so this goes a lot with our procedures as well and our ability to repeat. It can also depend on how clean our equipment is, various things as well. Repeat procedures. Okay, all right, so let's go into sig figs. Well, in lab, we have two types of numbers. We have the measurement numbers, and we have the guess numbers. Okay, so let's see how that works. Well, first off, if I have a line, here, okay, and I want to measure that line, okay? So I'm going to take my ruler and I'm going to put it into centimeters because I deal with centimeters the best. So first off, I'm going to line it up. I'm going to get the camera a little bit closer here so you guys can really see the accuracy and make sure our results are precise. Okay, so if I'm measuring this, I know that it is absolutely 5 centimeters. Okay. It extends beyond, doesn't quite hit 6, but I can know that it is 5. Okay. Point. Ooh. Okay. Well, if I count these little ticks, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know it at least goes to 9. So I know from this, based off this ruler, that it is 9. Now, at every one, you are allowed +1 guess on every piece of equipment. Okay? So, knowing that, it's kind of in between 0.9 and 6.0. So I'm going to guess that it's 0.97. Now this is where everybody's going to be different. Everybody's going to have different measurements. Everybody's going to see things differently, and that's why you as a scientist have to work on your measurement skills. So my final measurement would be 5.97 with my one guess right here, which is not labeled on my piece of equipment. Okay? Now, if I'm counting in terms of significant figures, I am assuming that these three are significant. So that tells me how accurate my piece of equipment is. If I have another number, for example, 5.784, I would assume that this one is guessed. So which piece of equipment is more accurate? Well, this one's going to be more accurate. Okay? So how do we determine significance? What is significance? Okay? So if I look at a set of numbers, there are several rules. First rule, all non-zeros are significant. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, zeros are where it gets tricky. Okay, so zeros between are always significant. So an example would be if I had 2.0 or 2.01, these two of course are significant as well as this one. If I have 200.3, all four of these would be significant. Why? They're actually holding a place. If you take out those zeros, that completely changes the numbers. Okay, so let's talk about when sometimes zeros are significant if following a decimal. Okay, so if I have the number 200, okay, I only have one significant figure because these zeros are following. If I have 200 point, all three would be significant. If I have 213.0, again, all three. That last one tells me how significant my piece of equipment is. Part of the reason why this one's not is you can easily put this number into scientific notation and it expresses the same thing. Okay? Those zeros aren't doing any good. Okay? They don't tell us accuracy because they are not accurate enough. But if I put my decimal there, then they are. The next one is zeros before are never significant. Okay? Okay? So zeros before are never significant. Now, why is that important? Well, let's take your paycheck. Let's say that you have a $200 paycheck. Okay? And we'll say 200.10. Okay? That's your paycheck. If I write this, it looks kind of better, but it's the same amount of money. So zeros in front are never significant. Okay? And in this case, all of these zeros are significant because they fall in between. If I put a 0 here, that's following a decimal. That would also be significant. Okay? So zeros before are never significant. Zeros between are always significant. And zeros following are significant only if there is a decimal. Okay? Now, how is this going to play in our mathematics? Because this is important. When we're in the lab, we're oftentimes taking data and we're using mathematical functions, so we still have to express in our final how important that information is. and how accurate it is. So in multiplication and division, the rule for dealing with sig figs is you always round to least number of sig figs. Example, let's say I'm trying to find density, which is mass divided by volume, and I go into lab and I find out that I have a mass of 6.00, and I have a volume, we'll say milliliters, or grams, silly me, and I have a volume of 3.0. So again, this would be my estimated, and this would be my estimated. This piece of equipment is less accurate, so my results have to reflect the less accurate piece of equipment. So my answer would be to how many sig figs? Well, this one had 2, this one had 3, so my answer is going to be into 2, which is 2.0 grams per milliliter would be my density. Okay, so that's how you use it. The same is true for multiplication. You always round. Again, you want to round up or down depending, of course, 5 you're going to go up. If it's less than 5, you're going to stay with that same number. For addition and subtraction, you're always going to round to least number of decimal places. Okay, so if I have, for example, I'm trying to add up molar masses, and I have 36.71, and I have 3.1, and I'm adding those up because they're going to be an AMU, which we'll talk about later. I'm going to have 1,893. Well, I round to the least number of decimal places. This one has 2, this one has 1, so my answer, therefore, in correct terms would be 3.98 AMU. Don't forget those units, because that shows us the accuracy of our results. Okay, hope you guys have had a great tutorial, and I know it's shaky on the first time, so we will keep working and keep getting better.